Now we're going to turn to our panel of Nobel laureates to share their predictions of how optics will ignite the future. Please welcome to the stage Bill Phillips, Nicolaas Bloembergen, Robert Curl, Jan Hall, Roy Glauber, W.E. Moerner, and Dave Wineland. Let me briefly introduce our luminaries one by one, and what I'm going to do is pose a question to each one of them that, after some very detailed negotiation, we've got them to agree to, or not. And what we're going to do is talk about the future, and the future might be 100 years, it might be tomorrow, and I'm pretty flexible on this one. And I'm going to start with Bill. Bill Phillips, along with Stephen Chu and Claude Cohen-Tanuji, won the 1997 Nobel Prize in Physics for development of methods to cool and trap atoms with laser light. And the question we thought about for Bill was, what theory being discussed today would change the way people live in the future? Bill.
Thank you, Peter. So first, I want to begin by affirming Professor Kaku's affection for that great American philosopher, Yogi Berra. What Yogi taught us about prediction guarantees that essentially everything that any of us say today about predictions very far into the future is essentially guaranteed to be wrong. And any overlap between what we say and what actually happens is going to be completely a matter of luck. So with that as background, let me tell you what I think is going to happen. What theory is going to be changing our lives in the future? Well, that theory is quantum mechanics. And you say, well, wait a minute, Bill, we've had quantum mechanics for 90 years, maybe 100 years, depending on how you count. And so much of our modern technology today is based in quantum mechanics. That's absolutely correct. So what's the deal? It's all happened already. Well, that's true, but almost all of the quantum mechanics that has become part of our technology has been a part of quantum mechanics that has ignored the weird and wonderful parts of quantum mechanics, namely superposition and entanglement, with a few exceptions. And I believe that now we are at the beginning of what I like to call a second quantum revolution, where we're going to get technology that depends upon those weird features. So what is that going to be? Well, things like quantum computers, things like quantum simulators are going to change our lives. Not because quantum computers will be able to factor big integers, which the spies are all interested in doing, not because quantum computers are going to do arithmetic better than silicon computers, but because quantum computers and quantum simulators can do something that those kind of computers aren't very good at, and that is solve complex quantum mechanical problems. And in particular, things like many-body problems, where the complexity of the problem produces a difficulty of computation that grows exponentially with the size of the system. Today in quantum mechanics, we come up mainly with ways of getting around that difficulty and making it look like single particle quantum mechanics. But there are some problems that don't yield to that kind of clever approximation. And what I'm hoping happens in the future is that we have quantum computers and quantum simulators that can solve difficult, complex, many-body problems in quantum mechanics that will lead to a discovery of new kinds of emergent phenomena, new kinds of materials, new kinds of devices that will change our lives in the same way that the devices we have in our pockets today have changed our lives, but in ways that we can no more imagine today than Niels Bohr would have been able to imagine mobile smartphones in 1913.
Bill, thank you. Fantastic. Wonderful. So our next luminary is Nico Bloombergen, who along with Art Schawlow received the Nobel Prize in Physics in 1981 for their contribution to the development of laser spectroscopy. And the question that we thought for Nico was, in the next 25 years, what tool or technology will become the norm in our daily lives that's absent today?
I would like to begin with the past, of which there can be no argument. The fact that everybody now communicates by email with anybody else in the world is due to two great developments in optics, namely very low loss fibers with laser amplifiers in there, and the signals we can send by picosecond semiconductor laser pulses. And these two together make that we have a World Wide Web communication system for this world. The second point is I want to re-emphasize the speaker who measured the LIGOs, laser interferometer gravitational observatories, who have demonstrated the existence of gravitational waves. And I agree with the main speaker that the Nobel Committee probably should choose some of the LIGO people in the next few years. And then the third item I want to discuss is two very large projects that are not so certain. In fact, one is certainly dead, and that's the Star Wars program of President Reagan, who used as his major scientific advisor Edward Teller. And in the 80s, and most of you were alive then, Star Wars was a very big social topic, and we don't hear about it anymore. And this sort of funeral of the Star Wars program was published in the Reviews of Modern Physics in the late 1980s by a study committee, not from the National Academy of Sciences, who was scared of this topic, but by a committee of the APS, American Physical Society. And Kumar Patel and I were co-chairs of that. And we wrote a report on the Star Wars and its future, which still stands after 30 years. Thank you. If I may have one more second.
Of course.
There is another very crucial item right now, and that is the Lawrence Livermore Lab on thermonuclear power. That wasn't mentioned by the speaker, and it's right on the balance of break-even. Break-even means that shining laser pulses onto a little mixture of tritium and deuterium in a heavy metal sphere, whether you get more power out from the way the sun produces our power, namely by thermonuclear fusion of hydrogen into alpha particles, whether we can reproduce that program here on Earth. Of course, if we succeed in that, then there are very difficult technological problems to raise it, but then all our future energy problems would be solved. And right now, Lawrence Livermore is very critical. Some people say they have reached thermonuclear balance, and some others say, no, we are not quite there yet.
Nico, thank you. Our next speaker is Robert Curl. Robert received the 1996 Nobel Prize in Chemistry, along with Sir Harry Kroto and Richard Smalley for their discovery of fullerenes. And Robert, what technological development is ready for transfer to the corporate or the public sector out of the laboratory?
When I saw this question, my heart sank. I had no idea how to answer it. But not being a quitter, I thought, well, who can I talk to that might feed me some information about this? And so my thoughts went to a friend of mine, Federico Capasso, who invented in the middle 90s the quantum cascade laser. And I collaborated with him and with one of my other colleagues, Frank Tittle, in applying these lasers to atmospheric monitoring. And so I first started by looking up what Federico had been publishing lately, and he had changed fields again, and he was publishing things about meta-optics. Now, meta-optics are the use of nanoparticles to alter the phase of light so that you can direct the far field almost any way you want to. And so specifically the things that Federico said, and I believe him because he's one of the smartest guys I ever knew, that what's ready to go is using lenses made with meta-optics in things like machine vision, which is a way of monitoring production by actually looking at objects as they are produced and feeding them to computers. The use of this in laser, I'm trying to remember the right word. And, no, it's thanks, but not the right answer. This is a situation where you scan what is that? You scan the beam of it's a macroscopic thing. So this is what? Yeah, confocal microscopy. Thank you, confocal microscopy. And the last thing was in laser. I have a terrible time. Laser lithography. You're focusing laser because you can focus with these lenses to very small, less than wavelength light. He has produces very high aperture lenses, and that's not the only thing you could do. That's the sort of thing that's just right off the shelf. The main issue is just setting up the manufacturing, which you can do with CMOS technology or with nanoprinting. Another thing that you can do right now, which is not a lens, you can do all sorts of things without using lenses. This is an inline polarimeter to measure the complete polar structure of laser light, which is very useful in operation of fiber optic circuits, because having the polarization correct is very important in that. The final thing that you can do, and this again is not a lens operation, is you can build a spectrometer which produces very high resolution with a single element in a very compact space, because you can get very high angle deflection of light and spread the spectrum very, very rapidly. And this is all done with a single, very small, compact unit. Now, those are things that are ready to go. They're not, the big deal is being able to replace all of the very complicated the ordinary lenses, which require quite a bit of polishing and construction, with relatively cheap, quite cheap, simple lenses that have very high quality. There are so many other things that you could do with light that are on the horizon, but they're not part of the answer to this question, because my question is very specific. What can you go start to manufacture right now? One is the thing that's there's a subject of one of Capassel's students talking about this afternoon at 4:30 in the vortices section, where he talks about the creation of sub-wavelength Bessel beams. And what this means is, unlike the ordinary beam from a laser, which expands as it goes away, may take a long time, but if I shined a light at the end of the room, it would be a much bigger spot than it is here. Bessel beams do not expand when they transmitted, because it's actually not there's a single center core and then waves on the outside, and the waves that are on the outside support its lack of diffraction. And another thing that Capasso is doing, I'm out of time. Is that, okay, I'll stop.
Our next speaker is Jan Hall. Jan and Ted Hansch were awarded the Physics Nobel Prize in 2005 for their contributions to the development of laser-based precision spectroscopy, including the optical frequency comb technique. And Jan, the question we dreamt up for you was, what idea being discussed today will change the way people live in the future? Jan.
I don't know how I came next, but I thought I would be on the end. Anyway, the ideas which I think are important is a lot of people here with huge energies, huge potentials. And this seems too deterministic, because we've already heard that some of the biggest discoveries are by accident. So what one needs to be aware of is something which, when I have calculated and when I've measured, and there's some difference, that's a place to look. That's kind of interesting. Now, one of these places, in my experience, was to make more beautiful lasers. For me, that means its frequency is, perhaps some of you would say it's totally boring. I would like to have the same frequency so that I could predict how many cycles I had. And let's say as a target for this discussion, it would be 1 minute. And now we're having 5 times 10 to the 14th cycles in 1 second. I'd like to know within a radian. Now, this is completely beyond what's possible, but it's very interesting, because if you could build interferometers or lasers stable on that, you'd be able to see really small distances like we were talking about in gravitational waves. Now, another place where lasers of a less perfection, but almost what we have now, is if you could get this same kind of precision, but get it into the smallness of how many waves was that? That was 10 to the 18th waves, perhaps. But if we could get one wave, which was 10 to the minus 15 seconds or 10 to the minus 14 seconds, this is really interesting. It just has one pulse. But if you repeat that, then you really have something going, because there's interference between the response that the system had from your first pulse, your second pulse, and even what your 1 millionth pulse. That's less than a second away. And this kind of optical comb, if you want to look at it in frequency, has really interesting properties. Now, as I begin to approach the entry point for middle age, medical things get interesting. And so the idea of being able to analyze what one's health is in a really non-invasive kind of way. I don't mind to take a little blood out, but I know that that's the wrong thing to do. Because if you think about it, this is a control system, walks around and weighs 100 whatever pounds, keeps its temperature pretty well regulated. But if you look in the blood, you're looking inside the control loop. Now, everybody that's built a controller knows that the error signal should be 0 inside there. There shouldn't be any variation whatsoever. If you can see any variation, it's really busted. But if you look in another stream, like the human breath, this is what the body says, I don't want any more of. And you'll be interested to know that if you measure your breath with this optical comb, well, if we don't have too much pressure that's Doppler width, and we can make a comb that would have, let's say, 3 or 5 lines across the Doppler line, and that would give us the possibility to find where the centers are and what the amplitudes are. And there's approximately 1 million of those comb lines across the spectrum that the laser makes, so we could resolve hundreds and hundreds of molecules. And it turns out that we emit molecules that you wouldn't have supposed. For example, did you know that in the basic air that we're breathing in, there is less than 1 part in 100 of special isotopes, like carbon 13 and 14 or oxygen 18. In the breath that we breathe out, it's almost equal, carbon dioxide, of these weird special kinds of things. Now, people that are in biology will say, oh, this is about molecular recognition. The body doesn't want anything to do with that. It's really interesting. I think it's screaming at us that there's something we're going to be able to find out by looking at our exhaust stack gases. Thank you.
Jan, thank you very much. Our next speaker is Roy Glauber. Roy received his Nobel Prize in Physics in 2005 for his contribution to the quantum theory of optical coherence. And the tortured question that we dreamt up for Roy was, what advice would you give to a student or new researcher on what in the future is worth really investigating?
Well, this can be a very short talk. I can't think of much, I have to tell you. I'm maybe unique among the 7 of us here in being a theorist and not an experimenter. And that leads me to see contradictions and problems that lie in the path of many of these suggestions. And I have to say of our featured speaker earlier, there's not an awful lot he said that I would agree with. A lot of it was charming, and I won't deny that. But looking into the future with any amount of plausibility, any real support, is very difficult. The one thing I can foresee, however, is that there ought to be a new organization formed for gravitational studies. The Gravitational Society of America is maybe what we should be working on now. I think with that I'll sign off.
I knew I wasn't going to get away with anything there. Never mind. Our next speaker is Dave Wineland, who, along with Serge Roche, won the Physics Nobel Prize in 2012 for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. And the one that we've dreamt up for Dave is the following. What technology that's in an early stage of development will be a game changer in the coming years? Dave.
Thanks, Peter. First of all, I wanted to say it's an honor to be here on this panel. I think OSA is, of course, a wonderful organization and is obviously very strong and has strong leadership. And this being the 100th anniversary is certainly a testament to that. I would also say that I'm an atomic experimentalist, and I benefit from this society for sure. I'm a laser user, not a laser developer, not an optics developer, and many of us, including our group, have benefited over the years from the work that comes out of the members of the society. So anyway, getting on to the question, I'm unfortunately following Bill Phillips, and I'm going to say some similar things. I think that because I'm involved in this business of quantum information, I think I feel I'm really very optimistic that there will be some good things come out of that. Of course, this got a big wave of support starting about 20 years ago now, mainly for the potential applications in cryptography. But I think I would also second what Bill was saying. I feel one of the really interesting things that's on the hopefully not too far horizon is this idea of simulation. Bill mentioned that, of course, the problem with simulating complicated many-body quantum systems is this exponential scaling in terms of memory and resources that you need to do simulations. And in principle, anyway, the quantum computer takes that because you're mapping the problem, one quantum system onto a quantum system, and that potentially gets you over this issue of the exponential scaling. And just to set some scale for this, I think the groups now, I mean, we're still kind of at the very start of this whole business, but the one thing to say is that some of the experiments now are reaching the point where they have enough quantum bits that they're approaching this threshold where we can no longer check what we're doing in the lab because our classical computers aren't powerful enough. And so that's one plateau that we can look forward to. The other thing is I think that so far the problems we're looking at, I think we pretty much know the answers to. We can simulate the problems on our classical computers. And where the real breakthrough will be, I think, is when we get to the point where we discover some new physics. And I'm optimistic about this in part because, at least for this simulation problem, I think we know what we have to do. The technological problems are there. And I think I often think about comparing to fusion plasmas where, I mean, people working on fusion energy, very smart people, but the system is extremely nonlinear and unpredictable. And I think the feeling in the community working on quantum information is that we do know what the technical problems are, and we have to solve that. And I think with the help of people like you in the audience, I think I'm optimistic we'll get there. I'm not sure I'd suggest investing in any quantum computer companies yet, but I am optimistic about the future of the business. So thank you.
Thank you, Dave. And I've saved up our last slot on here for our most recent Nobel Prize winner, in fact. The Nobel Prize in Chemistry in 2014 was awarded to W. Moerner, Eric Betzig, and Stefan Hell for the development of super-resolved fluorescence microscopy, an area that we've had referred to in the main talk of this session, in fact. And the question that we've dreamt up for WE is, what early stage technology will be a game changer in the coming years?
So thank you very much, Peter. It's a great pleasure and honor to be able to address you today. I too have great concerns about predicting the future. It's most likely that I'll be wrong. But nevertheless, I think that in the future, we will see many new devices and applications which take advantage of the interaction between light and single quantum systems in many new and very interesting ways, especially single molecules, but also single atoms, single ions, and defects in crystals. This particular technological area depends not just on physics, or not just on optics, or not just on engineering, or not just on chemistry, but actually all of these fields together. Think about it. We can use light to optically, from a distance, observe these single quantum systems like molecules or molecule-like systems. And this is an incredibly powerful concept because these tiny ultimate objects provide a window into the nanoscale, a window into the brain, into neurons, or a probe that lets us look in those environments, or a qubit, or a nanometer-sized light source even. So the current early stage work that's been going on, I think you know some aspects about it already. First, in recent years, it's been possible to optically control molecules that emit light, single molecules that emit light, by forcing them into and out of dark states. This can be done with stimulated emission depletion, but it also can be done with photoactivation, chemistry, or it can be done with other sorts of chemical processes to produce these on-off effects. New molecules are being designed already to enhance this optical switching, and we need better ways to do this. As many of you know, doing this with single molecules led to super-resolution fluorescence microscopy. But another critical area in which there's been a great deal of recent progress is the marriage of individual emitters or absorbers with metallic nanostructures. This approach, whether it's done with bow tie nanoantennas or other nanometer-sized metallic structures, greatly enhances the interaction between the far-field optical spot and the single quantum emitter. You see, the thing is, this is a hard thing to achieve because one of the objects is on the size of a nanometer, and the laser beam has a wavelength and the visible on the order of 500 nanometers. So in both of these cases, we are now only beginning to be able to sculpt the way in which light interacts with these nanoscale objects. At least the optical diffraction limit has been circumvented, but in the future, I really expect that a wide array of advances in the chemistry of controlling nanoemitters, as well as in the optical systems we are using to try to look at these individual objects. The result will be exciting applications of optics, for not only for nanometer scale imaging, but also extremely sensitive detectors of biological pathogens, or optical manipulation even of nanomotors. One of the advances that was recognized by this year's Nobel Prize in Chemistry, using light to make a molecule turn on the nanoscale. In a related area, single quantum objects, of course, with ground state spin, are being explored and used to produce quantum computations, and that area is certainly going to expand. So to push all these ideas forward, we need a very broad interdisciplinary view that is not hindered by traditional academic boundaries. A lot of people say, oh, well, he's a chemist, or he's a physicist. But in fact, we do all of these things at the same time these days. Physics on molecules, and engineering to control light. I believe there's no substitute for undirected, curiosity-driven, multidisciplinary research, and no substitute for continued funding for basic science, continued stable funding for basic science from our nation states, and also from business, to deeply explore new ways to control how light interacts with nanoscale objects, because this will provide the fuel for a wide array of new future inventions. Thank you.
W.E., thank you so much for that. We've got one last thing. Our first speaker, I'm going to turn to him now for a closing remark.
I'm not on yet. Okay. So listening to all these wonderful ideas about what's going to happen in the future made me think about a particular scientist, a friend, an innovator who has really changed what we are capable of doing some of these things in the future. Debbie Jin gave us the ability to work with atomic fermions, the stuff that most of the things that we're interested in the world are made of, electrons and all the fundamental particles. She gave us quantum degenerate fermions, which is the basis from which we are already doing so many amazing things, and I believe in the future will continue to do so many amazing things. So much of what happens in the future with quantum information, quantum simulation, is going to be based on the things that Debbie Jin gave us. Her death about 1 month ago at the age of 47 has left us bereft of one of the most important and wonderful scientists and human beings that I've ever known. And there's no chance that Debbie Jin is going to be forgotten, because the work that she did is going to infuse so much of what happens in the future. But I didn't want to leave this conference without mentioning what a wonderful scientific legacy and personal sense of friendship and engagement she has left us. Thank you, Peter.
Bill, thank you for that, because I think it's really worth remembering that the work of members of the OSA, and Debbie was a very dedicated member of the OSA, that work from all those efforts that you have put into our subject will change the world in ways that I'm sure are unimaginable and truly exciting. So thank you for all of you for contributing your thoughts on this. I'm deeply alert to the fact that we've positioned you right on the edge of a steep drop. I'm not sure about the OSA insurance, so do be careful of this edge. But there we go. Can I please thank all of our speakers now and invite Liz and Alan to return to the stage for the closing remarks.
So thank you, Peter. The conversation on the state of optics was very much appreciated and very timely. And I want to thank the audience for celebrating with us on this important occasion, and to thank the Nobel laureates. We greatly appreciate your time and your thoughts about what's happening both in the future and currently in our community. Given our focus on the future, we thought it would be only appropriate to invite the next generation of young scientists to help us hand out some gifts. So we have here Jonathan and Kate Ellis's daughter, Julia, who's 6, and we also have Ian and Lenore McMacken's son, Baz. Some of you might have met him at the party last night. And they're going to help us hand out some gifts. So, Julia, you can give your first gift to Jan. And Baz, you can go get some gifts over here. So you want to get another one? Here. One right here. And so this is a commissioned piece of glass. We met artist Harold Lustig, who created this. Is made out of dichroic glass, and it's been commissioned just for the centennial, and it's a beautiful piece of art, and we hope this shows a small token of our appreciation for you being here today. So for everyone here, maybe a round of applause for our young scientists and our Nobel Prize winners.